Okay, let's start our lecture today. We learned about hard margin support vector machine in the previous lecture. Hard margin was the case that data is linearly separable. We had two classes. It was binary classifier. We had two classes, and there's possible to have a linear decision boundary to separate these two classes perfectly. That was hard margin, and so we started from minimizing norm of the hyperplane subject to the constraint that beta transpose xi plus beta null times yi is greater than equal 1 for any I. And then we managed to write the dual form of this optimization problem, and it turned out that the dual form is a quadratic programming, a convex problem that we can solve and find the dual variable, and we know how to compute the primal variables in terms of dual variable. So we can get back beta and beta null. In fact, I'm not sure if I emphasize on that. Finding beta is trivial when you have the dual variable alpha, because beta is going to be sigma alpha I yi xi over all I. But what about beta null? How we can compute beta null? You solve the dual form of this optimization problem, and you have alpha. You have a vector of alpha for any point. Corresponding to any point, you have alpha I. So we know how to compute beta. How can I compute beta null? Any idea? If alpha is 0 for a point, the point is not on the boundary, not on the decision boundary. Margin. If it is equal, if it's greater than 0, we learned that the point is a support vector, right? Is on the margin. Being on the margin means that yi times beta transpose xi plus beta null is equal to 1. For those points that they have alpha greater than 0, for support vectors, yi times beta transpose xi plus beta null is 1. We know how to find beta. So for support vectors, we can solve for beta null. Right? We can find beta null. We also learned how to extend this to nonlinear cases by putting a kernel in the dual form. Instead of x transpose x, we can put a kernel. But I raised a question at the end of the previous question that if I have a kernel, in the dual form, in optimization, it doesn't matter. I can just replace x transpose x with kernel xx, right? But what about computing beta? Beta is sigma alpha I yi xi, right? Suppose that all points have been mapped to some feature space. Then this is phi xi. But we don't know what the phi is. We never knew explicitly what the phi is. We just implicitly computed phi transpose phi. We never knew that. So when I use kernel and solve for nonlinear case, how can I compute beta? Any idea? In fact, you have to ask yourself that do you need beta, or you just need to know the decision boundary? We compute beta to compute the decision boundary. We don't need beta itself, And decision boundary is beta transpose x plus beta null, right? Is beta transpose x plus beta null at point x. So if I'm in feature space, if I mapped everything in this Hilbert space, then all of x's are phi x. So this is beta, and this x is phi x, right? Now, the beta transpose would be sigma alpha I yi phi xi transpose. And phi xi transpose phi x is kernel. So you don't need to know phi. You can't compute beta, but you can compute the decision boundary, right? And that's the important part. We don't need to know beta. We do need to compute the decision boundary, and you can compute it here. So this is basically k, xi, and x. At any point x, xi goes from 1 to n. So basically, this is going to be similarity between all points and this particular point. It's a vector of length n that you sum over. Okay. So any question before we start soft margin? Yes?
When we are using phi x, is there any chance that the support vectors change from when you are transforming from space 1 to space 2?
Definitely they change.
So the betas will change. So
Yeah.
everything will change in the space. How
Sure.
can we use that beta from the first space?
No, we don't use the beta from the first space. No, we don't use it. We say that the beta is a new beta with phi, but we can't compute it because we don't know phi explicitly. But it doesn't matter because the only thing that we need to know is decision boundary. I want to classify points, I don't need to know beta. And to classify point, I need to compute beta transpose x. In this case, it's going to be beta transpose phi of x, and it makes a kernel again. Okay? I mean, decision boundary in kernel case is sigma over I, alpha I, yi, k, xi, x, plus beta null. Okay? Any question about hard margin classifier? Hard margin support vector machine? Okay. Now let's look at the case that data is not linearly separable. It's not possible to have a linear decision boundary such that data is perfectly separated, Okay, it means that, in hard margin, I had this decision boundary. I managed to compute some margin, and all points of one class was on one side of this margin and one boundary, actually, and a couple of points were on the margin. They were support vectors. And points on the other class on the other side, and some of them on the margin, support vectors. Okay? So that was our situation in hard margin. Now we have a case that it's not possible to have a perfect decision boundary. It's not possible means that there are always points that are on the other side. So you have this decision boundary, but there is one point from positive class, which is here. There's a point from positive class, which is here or here. And there are points from negative class, it's here. Okay. So it means that if I write this optimization problem, then I cannot satisfy this constraint. You know, we rescale the space such that margin is 1, and the distance of each point from the decision boundary is always greater than equal 1. It's on the margin or over the margin. Nothing is inside. Okay, nothing is less than 1. But we can't satisfy this anymore because there are some points that are going to violate this. You know, this is not a feasible problem. You know, if you try to solve this, it's not a feasible optimization problem anymore. So I need to change this constraint in a way and make it feasible. I have to take care of those points that violate the margin or violate the decision boundary. So how can I change this constraint to basically take care of those points that plan to violate my constraint? They're not more than 1. They could be here.
Look at the mean.
Sorry?
Look at the mean of each class
Okay.
and find the decision boundary that is far from both means.
Right. I mean, you're trying to basically come up with an algorithm to solve this. And what I'm asking now is just this particular constraint. How can I modify this particular constraint to accommodate these, you know, rebel points that wants to violate and go over the margin? So this point, for example, does not satisfy this constraint. It's not greater than 1. It's less than 1. So this shouldn't be greater than 1. It should be what? Any suggestion? Sorry? I can't start here.
Can we consider the lower bound and remove yi?
You mean lower bound of these points? So I don't know what the lower bound is. You know, I just know that some of them are going to go to the other side. So I'm sure that it's not greater than 1, right? So for some point it is, for some point it's not. So there are points that it's greater than 1 minus some positive value or some non-negative value. For some of the points, this is going to be positive. For some of the points, it's going to be 0. So I just define a new variable, zeta, that could be greater than equals 0. If it is 0, so I can accommodate, I mean, these are the situation that we had in the past that points are over the margin. But for some points, it's going to be greater than 0. It means that there are some points that are going to go to the other side. Okay? But if I just solve this optimization problem, you know, this constraint doesn't mean anything anymore. It's not really a constraint anymore, you know, because I allow points to be less than 1. You know, somehow I have to make a mechanism such that most of the point satisfy my original constraint and only few points violate. Only few points need this zeta to be greater than 0. Okay? So I can add a factor here to my objective function and basically penalize those points that are violating the constraint. So I let some points to go over, but there is always a penalty for that. If they go over, something will be added to my objective function. So I will basically add over, the sigma of all of these penalties, and that's just a coefficient, So if they are good points, they don't violate the constraint, this value is going to be 0 and nothing will happen here. But if they go over the margin or the decision boundary, then they need a positive value here, and this will be added to my objective function. And don't forget that I want to minimize this, It means that when I try to minimize this, it means that I don't like this happen often. I let it happen, but I don't want this really happen all the time. Okay? So I minimize basically the situation that this can happen. Okay, is it clear? So now we have a new optimization problem, and we can do whatever we did in hard margin and see what's going to happen. This is a constant. It's not a new variable. This is a new variable. So I can write a Lagrangian, exactly what we did for the hard margin. Now my primal variable is beta null. I have a new primal variable, this zeta. And I need to define some dual variables, right? Okay. So this is going to be minus sigma alpha I yi beta transpose xi plus beta null minus 1 minus zeta I. So I need this dual variable. I have another constraint here, In the past, we had only this constraint. We had n of them. And now I have another set of constraints, and also I have n of those constraints. So I need another term here, minus sigma over zeta I, and I need a Lagrange multiplier for that. So this is another dual variable that I need here. Okay, that's my Lagrangian, and I have to take derivative with respect to primal variable. As usual, set it to 0. Okay. But before I do this, let me expand this because it's going to be easier when we take derivative. I have alpha I, yi, beta transpose xi. I have alpha I, yi, beta null. I have alpha I, and I have alpha I, zeta I, and I have lambda I, zeta I. Okay, that's my Lagrangian. Take derivative of this Lagrangian with respect to beta and set it to 0. With respect to beta, this term is going to be beta, right? This is 0 with respect to beta. This is alpha I, yi, xi. This is 0, 0, 0, 0. So this is equal to 0. It means that beta is equal to alpha I, yi, xi. And we had this in hard margin as well, you know. We had exactly the same thing. So let's take derivative with respect to beta null. This is 0 with respect to beta null. This is 0. This is 0. This is sigma alpha I, yi, 0, 0, 0. This is 0. So we had this also in hard margin. Okay. Take derivative of L. I have a new primal variable, which I have to take derivative. This is 0. What about this one? Exact. 1 for one of them, or you know, this is gamma times zeta 1 plus zeta 2 plus zeta 3 plus zeta 4. Is basically it's gamma zeta 1 plus gamma zeta 2 plus gamma zeta 3. And you're taking derivative with one of those zeta. You're taking derivative with respect to only one of them. It's going to be gamma. So it's gamma. This is gamma. This is 0. This is 0. This is 0. This one is alpha I.
It should be negative. Because in the first equation, we were negative.
Thank you. So negative alpha I. What about this one? Minus lambda I. So gamma minus alpha I minus lambda I should be 0. Okay. Now I put all of these primal, I put all of these dual variables in terms of, in place of primal variables in my objective function. So basically, I replace beta with this sigma and so on. So for the first term, I have 1/2. I have beta squared, which is beta transpose times beta. And that's beta. That's beta. So it's alpha I, yi, xi transpose. Another sum alpha I, yi, xi. And you remember, you know, then we combine this in the previous lecture as two sums. Ij, alpha I, alpha j, yi, yj, xi transpose xj. That was this term. I have this term. I I just keep it because I can't do anything about it. I have this term, alpha I by I beta transpose xi. Beta transpose can come out of this summation. And I can put alpha I by I xi in place of that. So then I have alpha I by I xi transpose alpha I by I xi, which I can write it as alpha I y alpha I alpha j yi yj xi transpose xj. You know, we had exactly the same thing in hard margin case. Then I have this alpha I y I beta null. I can take beta null out, and summation of alpha I by I is 0. So this term is 0. Then I have summation of alpha I. Then I have this term. I'll just write it here. Alpha I zeta I minus lambda I zeta. Okay? Okay, so it is, you know, this term and this term, I can simplify, right? So I can write as summation over alpha I, 1/2 of this minus this, so it's going to be minus 1/2 summation over ij, alpha I alpha j, yi yj, xi transpose xj. So that's for this term, and this term, and this term. Okay. Now I have these three terms. You know, all of them have this zeta. And if I factor this zeta, I can write it as plus gamma minus alpha I minus lambda I zeta. Okay? So it's this term, alpha minus gamma minus alpha minus lambda. This is 0. So this is 0. So my objective function is sigma alpha I minus 1/2 sigma alpha I alpha j yi yj transpose xi transpose xj. Is there any difference between this and the objective function that we had in the hard margin case? It's exactly the same objective function, right? We had exactly the same objective function in hard margin. So my objective function would be alpha I minus 1/2 sigma over I and j, alpha I alpha j, yi yj, xi transpose xj. So far it's exactly the same as hard margin. But one of the constraints in hard margin was that alpha I should be greater than or equal to 0. Now I added, because that's my dual variable, I added another dual variable, lambda. So I have to add this constraint as well. I have to say that lambda I should be greater than or equal to 0, because it's a Lagrange multiplier. Okay? But see, there is no lambda here. So what does this mean, that lambda I should be greater than 0? So lambda I has to do with alpha and with lambda. Because I know that, you know, gamma minus alpha I minus lambda I is equal to 0. It means that gamma minus alpha I is equal to lambda I. So if my constraint is that lambda I is greater than equal 0, it means that gamma minus alpha I is greater than equal 0. And this means that gamma is greater than equal alpha I. Right? So alpha I is greater than equal 0 means alpha is less than equal gamma. So it implies lambda I is greater than equal 0 implies that alpha is less than equal gamma. Is it clear? Yes? Okay. So see, my objective function and my constraint now would be alpha I over all I minus 1/2 sigma ij alpha I alpha j yi yj xi transpose xj. So far it's exactly the same as hard margin. Alpha I should be greater than equal 0. Lambda I should be greater than equal 0, but lambda I greater than equal 0 means that alpha I is less than equal gamma. That's the only difference between hard margin and soft margin. So in soft margin, I just have a new set of constraints. So alpha I in hard margin should be greater than equal 0. Now I add another constraint on it that it should be less than equal gamma. And gamma was, the constant of the penalty function that we added to objective function. So we're going to choose that gamma. It's a constant that you choose, If you look at there, the larger the gamma is, you are going to penalize this more, right? Okay. So that's basically our objective function and our optimization problem. Again, it's quadratic programming. The objective function is convex, quadratic. Constraints are linear. I just have a new set of constraints, so I can solve it efficiently. And it's convex. There is a global minimum for that. Okay. Now, what would be the concept of support vector? In the hard margin, we learned that if alpha is 0, so these points are over the margin. If alpha is non-zero, they are on the margin. So what can we say about the value of alpha now in this case? So let's look at the KKT condition again. So if we look at KKT conditions, we need to make sure that derivative of our Lagrangian with respect to primal variables is equal to 0. So this is 0. This is 0. And this is 0. Okay. So we have to check the primal feasibility. And the primal feasibility means that these constraints are satisfied at the optimum point. Means that yi beta transpose xi plus beta null is greater than equal 1 minus epsilon I, and sorry, it's not epsilon, zeta I is greater than equal 0. So that's primal feasibility. And dual feasibility means that alpha I should be greater than equal 0, and lambda I should be greater than equal 0. These are my dual variable. or Lagrange multipliers, they should be greater than or equal to 0. Okay, so what about, that's 3. What about complementary slackness? Complementary slackness, this dual variable times corresponding constraint should be 0, right? So it means alpha I times yi beta transpose xi plus beta null minus 1 plus zeta I is equal to 0. And also this dual variable times its corresponding primal variable should be 0. So it means that lambda I zeta I is equal to 0. Okay. So let's look at these two conditions now and see what does it mean in terms of the value of alpha. If alpha is 0, I can't say anything about this. But if alpha is greater than 0, then this should be 0, right? Okay. So suppose that alpha I is greater than 0. If alpha is greater than 0, then this implies that yi beta transpose xi plus beta null minus 1 plus zeta I is equal to 0, or means it's equal to 1 minus zeta I. Okay, so there are two possibilities. Either zeta I is 0, or this zeta I is greater than 0. Let me start from this one. If zeta I is greater than 0, if this is greater than 0, what can I say about lambda? It's 0, right? So if zeta I is greater than 0, it means that lambda I is equal to 0. Okay, if lambda I is equal to 0, don't forget that we had this condition that gamma minus alpha I minus lambda I is equal to 0, right? That was one of the conditions in KKT that we had to satisfy. So lambda I is 0. So it means alpha I is equal to gamma. Okay. So in the case that alpha I is greater than 0, there are two possibilities. One possibility is that this point is right on the margin. This is 0. One possibility is that this point violate the margin, cross the margin, go inside when this zeta is greater than 0. But if zeta is greater than 0, it means that alpha I is equal to gamma. For those points that have alpha I greater than 0, some of them have alpha I equal to gamma. Those points are points that violate the constraint, the original constraint, and go over the margin, and may even go over the boundary. You know, they might be on the right side, just violate the margin, but they might go to the wrong side even. You know, but these are those points. Okay. So what about this case? If gamma, I mean, if zeta is equal to 0, then lambda I might be 0 and may not be 0, right? I can't say for sure that lambda I is equal to 0 or is not equal to 0 because, I mean, the condition is satisfied by zeta being 0. But lambda I can choose to be greater than 0. It's not necessary for lambda I to be 0. So lambda I could be greater than 0. So if lambda I is greater than 0, it means that gamma minus alpha I is greater than 0, right? Gamma minus alpha I is greater than 0. And it means that gamma is greater than alpha I, or alpha is less than gamma. Okay. So for those points that have alpha I greater than 0, they could be on the margin, and in this case, alpha I could be less than gamma. But they could be, they may violate the margin, and those are that have alpha I equal to gamma. I mean, from this, I mean, this is not, from this conclusion, there is a could be here that alpha could be greater than alpha I, but if you combine these two together, you can conclude that for sure they are less than alpha, you know? Because there are two cases. Either they violate the margin or they don't. If they violate the margin, for sure their alpha is gamma. If they don't violate the margin, their alpha could be less than gamma. Could be less than gamma. Right? If they violate, could be less than gamma means that there's possibility that they are equal to gamma as well. But we know that if it's equal to gamma, for sure they violate the margin. So it's not going to happen, actually. So you have points with alpha I greater than 0. These are your support vectors. These are points that are important in optimization. Alpha I greater than 0. So among these points that have alpha I greater than 0, some of them violate the margin, those that have alpha I equal to gamma, and some of them don't, and these are the points that have alpha I less than gamma. They will stay on the margin. Okay? So in this scenario, you know, this is a support vector. In hard margin, it was a support vector. This is a support vector, but this is also a support vector. This is also a support vector. This is a support vector. This is a support vector. Oh, no, sorry. You know, just on the right side, this is a support vector, and this is a support vector. You know, those points that are on the margin, they make decision about decision boundary. Those points that they want to violate also make decision about the decision boundary. And all other points have no role here. You know, there is a difference between learning of V as human being and learning of machine. You want to teach a computer to make distinction between 2 and 3, and you need 1,000 examples, right? You want to teach a kid to what's the difference between digit 2 and 3, and you need one example. This is 2, this is 3, and they learn. This is table, this is chair, they learn. But you need 1,000 example in deep learning, in deep neural network. You need millions of examples for the model to learn. one lesson here is that in really, to learn this decision boundary, we just need a couple of examples, not really that many. These points have no effect on the decision boundary. If I had only these couple of 3 examples, I could have learned the decision boundary that I have learned with thousands of points, okay? But the bottleneck actually here is that I need to solve the problem up to the end and to see which points are important, which points are not important. So it's an important open question that can you decide ahead of time about important examples? It's a question not about support vector machine, a question in general. That can you decide about good examples for learning? That give me these examples, I give you a good class where I can learn a good class for free. Okay? I don't need to see everything. Okay, any question? Okay, see you next week.